In this video, we will be designing a dynamic programming solution for the knapsack without repetitions problem. Recall that in this problem we are given a single copy of each item. So this is also to remind you the formal statement of the problem. So we emphasize once again that we are not allowed to take more than a single copy of each item. Well, we already know that our previous algorithm cannot produce the right answer for our new variant, namely for the knapsack without repetitions problem. Well, this is simply because in our toy example, the optimal value for the knapsack with repetitions was 48, while the optimal value for the knapsack without repetitions was 46. So this means that if we just run our previous algorithm, it will produce an incorrect result. Still, it is important to understand where our algorithm or where our reasoning more generally fails for this problem. So once again, let's consider an optimal subset of items for a knapsack of total weight capital W, and assume for the moment that we know that it contains the nth element, that is, the last item. So we argue, well, similarly to the previous case, that if we take this item out of the current knapsack, then what we get must be an optimal solution for a knapsack of smaller weight, namely of total weight capital W minus Wn. So if we take this smaller solution and we add the nth item to it, we get an optimal solution for the initial knapsack of total weight capital W. Assume, however, that the optimal solution for the smaller knapsack already contains the nth item. This means that we cannot add another copy of the nth element to it, right? Because then the resulting solution will contain two copies of the nth element, which is now forbidden by the problem formulation. So this is why we need to come up with a different notion of a subproblem. So still, let's take a closer look at our optimal solution. It is not difficult to see that there are only two cases. Either it contains the last item or it doesn't contain it. Assume that it contains. And let's again take this nth item out of our current solution. So what is left? First of all, it is some solution for a knapsack of total weight capital W minus Wn. And it also uses only items from 1 to n minus 1. Because, well, we just took out the nth item, right? If, on the other hand, the initial optimal solution for the knapsack of total weight capital W does not contain the nth item, well, then it contains only items from 1 to n minus 1, right? Well, this simple observation will help us to get the right definition of a subproblem for this version of the knapsack problem. Well, on the previous slide, we argued as follows. Consider an optimal solution for a knapsack of total weight capital W. And there are two cases. Either it contains the last item or it doesn't contain. If it contains, we can take it out and reduce the problem for a smaller knapsack using only items from 1 to n minus 1. On the other hand, if it doesn't contain the nth item, then we reduce it to another case when the knapsack only uses items from 1 to n minus 1. In any case, we reduce the number of items, and in the first case, we also reduce the size of the knapsack, the total weight of the knapsack. We might continue this process and express the solution for all two subproblems through solutions to four sub-problems. If we continue in the same fashion, what we get somewhere in the middle is a solution for a knapsack of some weight that uses some first I items. Well, let's just use this as a definition of our subproblem. Namely, for any W from 0 to capital W and for any I from 0 to n, let's denote by value of W and I the maximal value that can be achieved by using only items from 1 to I and whose total weight is at most W, right? then it is easy to express it through solutions for smaller subproblems. Once again, value of W and I is a subset, is the optimal value of a subset of the first I items whose total weight is at most W. So we know that in this optimal subset, either there is the ice item or the ice item is not contained in it. So there are two cases. So we need to select the maximum out of two cases. In the first case, if we take the ice item out, what is left is an optimal solution for the following problem. We are allowed only to use the first I minus 1 items, and the total weight should be no more than W minus Wi. So this is the first term under the maximum. In the second case, if the ice item is not used in an optimal solution, then we just know that the optimal solution is the same as for the knapsack of total weight W, using only the first I minus 1 items. So we managed to express the solution for our problem through solutions for smaller subproblems. And this is probably the most important thing in designing dynamic programming algorithms. We now turn our recurrent formula into a dynamic programming algorithm. As usual, we start from initialization. Namely, we first set all the values of 0j to 0 for all j, and all the values of w0 to 0. Well, this just expresses the fact that if we have no items, then the value is 0. Or if we have the knapsack of total weight 0, then the total value is also 0, of course. Then recall, now we need to somehow compute all other values of wi. Recall that we expressed value wi through values of w, smaller w and I minus 1, and w and I minus 1. This means that we always reduce the problem from wi to something with smaller number of items, to I minus 1. This actually helps us to understand that it makes sense to gradually increase the number of available items, and that this is why we have in this pseudocode an outer loop where I goes from 1 to n. When I is fixed, we will compute all the values of wi. So for this we also go from w equal to 1 to capital W and do the following. So now I and w are fixed. We need to compute value of wi. First, we just check what is the value of what is the solution for the subproblem when we use the knapsack of the same weight w, but we only use the first I minus 1 items. This is implemented as follows. We first just assign value of wi to value of wi minus 1. Then we need to check whether we can improve this value by using the ice item. First of all, we can only do this if the weight of the ice item does not exceed the weight of the current knapsack, which is just w. So if it doesn't exceed, we see what happens if we take an optimal value for the knapsack of total weight w minus wi that is filled only by elements from 1 to I minus 1 and add the ice element to it. If this gives a larger value than we currently have, we update value of wi. So in the end, we just return the value of capital W and n, because this is the solution to our initial problem. So this is the solution for a knapsack of size capital W that uses just all the n items, right? Now, so it is clear that this algorithm is correct just because, well, it directly implements the recurrent formula that we already discussed. So let's analyze its running time. It is not difficult to show again that its running time is actually the same. It is again n multiplied by w. Well, this is again just because we have two loops here. So this is the first loop with n iterations, and this is the inner loop with w iterations, and what is going on inside only takes some constant time. Now let's apply the algorithm that we've just designed to our toy example. Recall that we need to store the values of all subproblems for wi for all w from 0 to 10 and all I from 0 to 4 in our case. For these purposes, it is natural to use a two-dimensional table or two-dimensional array. You can see such a two-dimensional array on the slide already filled in. So here we have I, so all the rows of our columns are indexed by all possible values of I, and all the columns are indexed by all possible values of w. Right? We start by initializing the first row and the first column of this table by zeros. That is, we fill this row by zeros, and we fill this row, this column by zeros also. Then we start filling in this table row by row. That is, we first fill in this cell, then this cell, then this cell, then this cell, and so on. So we go like this. So we first fill in this row, then fill in this row, then fill in this row, and then fill in this row. So the resulting value 46 is actually the answer to our initial problem. Now let me show you how some particular value, just to illustrate, let me show you how some particular value in this table was computed. For example, consider this cell. So formally, this is value of 10 2, which means that this is an optimal value of a knapsack of total weight 10 that only uses the first two items. So assume that we don't know what to put here. So we just need to compute it right now. So let's argue as well as we did before. So this is a knapsack of total weight 10 that uses only the first two items. Well, we then say that the second item is either used or not. So if it is not used, then this is the same as filling in the knapsack of total weight 10, just using the first item. And we already know this value because it is in the previous row. So this is value 10 1. Right? So the value in this case is 30. On the other hand, if the second item is used, then if we take it out, what is left is an optimal solution for a knapsack of total weight 10 minus 3, because 3 is the weight of the second item, which means that it is an optimal solution for a knapsack of size 7, of total weight 7, that only uses the first, that is only allowed to use the first item. Also, if we add this item to, if we add the second item to this solution, we get 30 plus 14, which is much better than without using the second item, right? So that's why we have 44 here. And also for this reason, we fill this matrix row by row. So note that when we need to compute the value of this cell, we already have computed the value of these two cells. So that's why we fill our matrix exactly row by row. Now, let me use the same example to illustrate an important technique in dynamic programming, namely reconstructing an optimal solution. By reconstructing an optimal solution in this particular problem, I mean finding not only the optimal value for the knapsack of size of total weight 10, but the subset of items that lead to this optimal value itself. Well, for this, we first create a Boolean array of size 4. In this array, we will mark for each item whether it is used in an optimal solution or not. Now, what we're going to do is to backtrace the path that led us to the optimal value 46. In particular, let's try to understand how this value 46 was computed. Well, first of all, 46 is formally value of 10, 4. That is, this is the optimal value for a knapsack of total weight 10 using the first 4 items. We argued that the fourth item is either used or not. If it is not used, then this value is the same as the value 10.3, which is shown here. That is, the value of the knapsack of the same weight using the first 3 items. If, on the other hand, it is used, then what is left must be an optimal solution for a knapsack of size 10-2, which is 8, that uses also the first 3 items. Well, this value is already computed. It is 30, so we need to compute the maximum among 30 plus 9, because, well, the value of the last item is 9, and 46. In this particular case, the maximum is equal to 46, which means that we decided at this point not to use the last item, right? So we put 0 into our Boolean array to indicate this, and we move to this cell. Again, let's try to understand how this value was computed. It was computed as the maximum value of two numbers which depend on the following values. So either we do not use the third item, then it is the same as the value of this cell, or we use the third item. In this case, what remains is the knapsack of size of total weight 6, and using the first 2 items, and its value is 30, plus the weight of the third item, which is 16. In this particular case, 30 plus 16 is larger than 44, which means that this value 46 was computed using this value. This in turn means that we decided to use the third item. Let's mark it by putting 1 into our Boolean array. Now we stay in this cell and we try to understand how it was computed. It was computed as the maximum over this 30 and this 0 plus 14, right? In this case, the first value is larger, so we move to this cell and we mark that we decided not to use the second item. Okay, and finally we realize that we arrived at this value 30 from the left upper corner, right? So this way we reconstructed the whole optimal solution. Once again, we backtraced the path that led us to the optimal value. Here, what is shown here is that we decided to use the first item and the third item. So let's check that it indeed gives us the optimal value 46. So indeed, if we compute the sum of the weights of the first and the third item, it is 10, and while the total value is 30 plus 16, which is 46 indeed. And as I said before, this technique is usually used in dynamic programming algorithms to reconstruct the optimal solution.